you just okay. So we want a kind of transformation that takes old coordinate and momenta and creates a new coordinate and momenta. So that's the basic idea of making a transformation in phase space. So problem is here when you try to make a coordinate transformation like that, if you do not do anything, like if you do not impose any specific condition, you might end up having like changing your Hamiltonian equation of Hamiltonian motion, like Hamilton's equation of motion as well. So we do not want that. So we want to make a kind of coordinate transformation that preserves the form of Hamilton's equation of motion. That's the basic idea. So is there any question so far? I think it's a little bit conceptual thing, so I should go a little bit slowly at this point. So if we are not comfortable with the concept of phase space, then I think we should like do some problem and understand our phase space a little bit better. So let me ask you a question. So let's consider there is a one-dimensional particle, like you have released from somewhere, some height h, and it's moving downward. So I'm considering this coordinate as my y, like this vertical coordinate as my y, and this specific height is h. So what would be the phase space diagram? So if I plot it here like y and py, like the corresponding momentum, so what would be the phase space trajectory here? Any idea?
It's falling.
It's falling, yeah.
Yep.
So y should be going in negative direction, right?
Right.
And also y starts with a value h, so probably somewhere here, right? But what is the value of momentum if we just release it from there? What is the value of momentum at that point?
It increases.
0. So it starts from here, right? It starts from there. And how does it evolve? So we can try to remember one thing, that Hamiltonian for this system is like half py squared divided by m plus mgy, right? Hamiltonian for this system. And this Hamiltonian is conserved, so it's just a number. So what is the relation between y and py?
It's the square root of minus. Oh, yeah.
Yes, yes. So if we write like h as a constant, E equals to h, like that's basically the total energy. So then half py squared divided by m equals to E minus mgy, right? And if you take a square root and multiply by this stuff, so then you get py equals to twice m e minus twice m squared gy and square root of that thing. So what would be the curve for this?
The curve. No.
So it will start from here because initial condition says so, and it goes like a square root curve, right? Like that. Oops. Like that. Also, it has a other branch like this one because it could be plus minus. But here actually we need to pick which one is true. Which one is true? Does py become positive or negative?
Negative.
It becomes negative, more and more negative, right? So this branch is not true as well, basically. So it should be this one. But the upper one is also a possibility. Huh? Do you agree?
Yes.
Okay, so what happens of phase space in a harmonic oscillator? So we know harmonic oscillator have a Hamiltonian like 1 over twice m p square plus half kx squared. So what would it look like? This thing is a constant. So what would it look like on a phase space plot?
Ellipse.
It would look like an ellipse. Yeah, like that. Because it has p square as well as x squared. So as you can see, like we can, for any system, we can plot actually this kind of phase space diagram and understand the physics out of it. So we are actually changing the coordinate on this phase space. So like what happens instead of setting this p and x as momentum coordinate, we just set up a new coordinate that treats, say, this angle as a coordinate, say phi, we call it, and this distance as the corresponding momentum, um, um, like pi. So then in that transformation, we actually go from xp space to a new space that actually denoted by this, right? So this is the coordinate transformation we want. This kind of coordinate transformation we want to perform. Is that clear to you already?
Yeah.
Yeah.
Okay. So if we are on the same page, then we're ready to proceed. So remember, our goal is to find a method of transforming this phase space coordinate like QK, PK. QK is the momentous, old momentous we call it, and PK are the old, QK are the old coordinates and PK are the old momentous. So we want to make a coordinate transformation like phase space coordinate transformation that creates a new coordinate QKs and new momentous PKs. And also we want to preserve our Hamilton's equation of motion. So say your Hamiltonian, old Hamiltonian that was dependent on Q's and P's, it becomes a new Hamiltonian, usually known as, mathematicians call it Hamiltonian. So it's basically transformed Hamiltonian, the better way to say it. So it becomes this. So we want equation of motion for K to be like this: delta K over delta Q, QK should be negative PK dot, and also delta K over delta PK to be QK dot. This is our goal. So we want to make a coordinate transformation, and that would automatically transform our old Hamiltonian into a new Hamiltonian. And we want the equation for the new Hamiltonian to be exactly of the form that it was in the previous case for H.
Yeah.
Okay, so question is, how do we do that? Because it seems our the definition of momentum is kind of twisted with the definition of coordinate itself. Like in Lagrangian, we had, if we even before starting with Hamiltonian, we had to find Lagrangian, right? Lagrangian of Q, Q dot, and most possibly T, like that. So definition of pk is already twisted into like definition of coordinate itself, it seems.
Yeah.
Right? So whenever we change our coordinate qks to a new one, do we have any like any freedom to choose our pks, or it's automatically fixed? In this formula, you
It's
just
fixed.
it's changed. So how do you do that? Like basically, we're trying to tweak both together. Like we want to tweak our qks and pks independently. So how do we do that? Is there any freedom to us? Remember one thing, our Lagrangian wasn't unique, right? Our Lagrangian could be transformed as well into a new Lagrangian, that is old Lagrangian plus a total time derivative of a function that is dependent on coordinate and time only.
Yeah.
So we can use that actually here. So how? So if you expand like df over dt, we get L plus delta f over delta t plus delta f over delta qk dot, right? Or let's write I, like that. So what happens in that case, our momentas, when we make this kind of changes, so our momenta pk prime would be delta L prime over delta qk dot. That would be just delta L by delta qk dot plus if you take derivative of f with respect to qk dot, that vanishes, but this term has qk dot, qi dot inside of it. So that part gives us delta f over delta qk, right?
Yes.
And as you can see, this thing is related to our old code, old momenta, like this pk plus delta f by delta qk. So yes, we can tweak our momentum independently only if we also tweak our Lagrangian itself, or like change our Lagrangian a little bit by this total time derivative part.
Yeah.
So all it means that our definition of Lagrangian is not unique, so as the definition of momenta, those are not unique as well. So if you tweak your Lagrangian, your momentum is already tweaked.
Yeah. Yeah.
Okay, so let's start with our Hamilton's principle. Hamilton's principle say that a particle follows that trajectory on which the action is minimized. So the definition of action itself is what? What was the definition of action?
Lagrangian
Integration
integration of
T1 up to T2,
T1 up to T2.
Lagrangian of Q dot
T.
and most possibly T dt.
Yeah.
This was the definition of Lagrange action itself, right?
Yeah.
We change our action a little bit. Actually, no. We can write it down in terms of Hamiltonian first. So in terms of Hamiltonian, it would be T1 up to T2. Instead of L, we have to write PK QK dot, like last day we saw, PK QK dot minus H, which is a function of Q, P, and most possibly T. Remember, when I am writing like inside of this parenthesis that Q dot and T, it means Lagrangian is dependent on all coordinates, most possibly, and is a function of all velocities. Same thing like here. We need not to write like h of q of h of q k p k like that. This is sufficient. What I have written.
Okay.
Happy?
Yeah.
So how about we change our action a little bit by a fixed number. So we call it S bar, which is defined as the previous S, this one, plus a number that is actually this thing. Integration T1 up to T2 df over dt, where f is a function of q, p, and t.
Yeah.
We can do that, right?
Yeah.
So okay. Last day we derived our Hamilton's equation of motion. So to proceed this, we actually first understand how like variation works here, like variation of S, how works that here. First we need to understand, then we'll do variation on S bar as well. Okay, so let's do a variation on S because we need to know a little bit more about it. So delta S, if we take variation on S, that gives us variation on T1 pk qk dot minus h as a function of q, p, and t dt. So how do you do the variation? So it's the integration is taken over t1 like time, and variation is a totally independent thing. So we can take that inside of the integration and proceed like that, t1 up to t2, and then qk dot variation of pk plus pk variation of qk dot, right?
Yeah.
And then we can have like minus h, so delta h over delta qk variation qk, and then minus delta h over delta pk variation pk. So I want to do the integration by parts explicitly, and I do not want to make it vanish at this very moment. So I want to see what's the boundary term where. So that's the basic idea of doing all of this stuff. So we get T1 up to T2, and then let's do the variation of PK first. Then we have QK dot minus delta H by delta QK. Sorry, delta PK I should write. PK variation PK plus then what?
PK.
We need to do the integration by parts. Yeah. So PK, then
PK minus
delta H by delta QK, right?
Yeah.
No.
No.
Negative PK. This is negative PK because actually we need to show the integration by parts here, right? We need to show the integration by parts here explicitly. So if you perform the integration by parts on this term, what happens here is, so integration pk variation qk dot dt. So it gives you, so take integration over the qk, so it gives you pk variation qk evaluated at t1 up to t2 minus integration t1 up to t2 pk dot variation qk dot qk dt. So we are talking about this part, so that gives us negative pk dot negative delta h by delta qk, and then we have variation qk, right, dt. Then we have the boundary term, this part, that is that actually vanishes as well, like pk variation qk evaluated at t1 up to t2. It vanishes because like variation at qk vanishes at t2 and t1 as well.
Yeah.
So this is the usual form of varying s. So what happens when we vary our f, like s bar, like the other one, like this thing? Point is, this basically a number, nothing else, right?
Yeah.
A constant value.
Yeah.
At initial time, you just put the corresponding position and momenta, so you get initial values. But whenever you are varying s bar, so this part doesn't give you anything more, but varying s gives you the equation of motion itself. So varying s bar and varying s should be equivalent, right?
Yeah.
Because s bar is just translated by a little number, a number only.
Yeah.
So let's vary our the other one, like the variation of s bar. What should it give us? So by varying s bar, first we should have the same variation of s plus variation of this thing, this thing, right?
Yeah.
Okay, so all we need to know what happens when we vary this other part. So, okay, yeah. So time derivative and time integration, these are totally independent. So we can write variation of s, basically the this term, actually this whole term, plus variation of f evaluated at t1 and at t2, like that. Where f is a function of q, p, and t. So let's substitute everything and see. If you substitute this upper part, like variation of s, you get obviously the equation of motion part, like integration t1 up to t2 qk dot minus delta h by delta pk variation pk plus minus pk dot minus delta h by delta qk variation qk, and then dt, and then this boundary term, the last term, that is plus pk variation qk evaluated at t1 up to t2 minus t1, and then we have this f part, That
Is not
is,
the last term is 0?
yeah, it's 0, but we are not writing it explicitly. We are going to use that actually.
Okay.
So we are trying to make use of that 0 part actually.
Okay.
So plus f. Actually, I have a shift of notation here. Like I should have instead of adding this term, I should have subtracted something. So like I wanted a minus term, that would be convenient. Is that okay with you guys?
Yeah. Yeah. We are
So
also
instead,
considering the variation of f at T1 and T2.
yeah. So I just want to make like shift of notation. It's nothing more, like you can redefine your f and absorb this minus sign, and that's okay. It's basically convenience for derivation, nothing else. It doesn't change anything. Also, you'll get the same result if you keep with that. So I want to make a negative sign over there. That's all. You can always redefine your f to be that absorbs that part. So it gives you this thing, minus variation of f and evaluated at boundaries, right?
Yeah.
Yes.
So as you can see, this first part, this produces the equation of motion, right?
Yeah.
This part produces the equation of motion. So like this, T1 up to T2. Actually, I need to repeat it. Okay, let's do it. I'm just going a little bit slow because this part is conceptually hard. So it's better to understand what we are doing. And if you have any question, please ask. Otherwise, I don't know that if you are following or not. So this is that part. And also we have a boundary term, that is pk variation qk minus variation f evaluated T1 up to T2, like that. Point is, we want to make a transformation. We want to make a transformation such that, so our coordinate, like old coordinate and old momenta, qk's and pk's, becomes new coordinate and new momenta. New coordinate like big qk and big pk, such that this term that this term like pk variation qk minus variation f, this terms is equals to, like this term becomes only qk, only pk big pk variation big qk. We want to make a transformation that preserves this thing. That's the goal.
But I have a question.
Yes, sure.
What is the motivation of this transformation?
Okay, so if we can keep this part preserved, then as you can see, it's basically pk variation qk, right? The other part is actually part that produces the equation of motion. So it will automatically preserve the equation of motion, like Hamilton's equation of motion. So that's the idea.
Okay.
So as you can see, as I discussed earlier, so whenever you change your coordinate, small qk, your pk's automatically changes, right? So we are actually choosing a new f and also changing our qk and pk in such a manner that this whole thing becomes pk variation qk.
Yeah. Yeah.
Okay, so if we can find a transformation that just only do that pk variation qk minus variation f, that gives you this part. Then what happens? That's actually what happens to this Hamilton's equation of motion. So that's the biggest question. So we have to make sure that our transformed Hamilton's equation of motion are also the same in the form. So we need to check that as well, that if we can make this kind of transformation, that works or not, right? So expand your variation of f and variation of big qk. Remember, in our transformation, it's a more generic one. So we are at, like when we are writing this arrow, we actually mean new qk's, new coordinates are actually function of old coordinates, old momentus, and most possibly time. So our coordinate transformation could be in principle time dependent. Also, we are considering our new momentus that are also dependent on old coordinate, old momentus, and most possibly time, like that. When we are writing just this arrow, then we actually mean this.
Yeah.
That's all. That's the usual form of, like, whenever we write a coordinate transformation, we write like that. So considering this thing, and also f is a function of qp and t, we explicitly write this thing, like this thing, in terms of those variations. So let's write those, what happens. So pk variation qk minus variation of f. How do I write that? So that is basically delta f over delta qk, variation qk.
Yeah.
And then minus delta f by delta pk, variation pk.
Yeah.
And on the other side, what do we have? Big pk, that's fine. What happens to variation big qk according to this relation?
According to this relation, it will be delta qk by delta p,
qk by
delta q
delta q
times the variation of delta
j.
uj.
Let's write j. Also, actually, do the other way. Instead of writing pk over here, this sum we can write in terms of other index like j, right? Let's write that. That would be easier, because we want to compare those. So let's be a little bit careful about indices. So this is one thing, and then delta qj over delta small pk, variation pk.
Yeah.
Okay, so now as we are tweaking pk and qk, like small pk and small qk totally independently, we set the coefficient of each of the variation to be 0. So equating coefficient of qk's, what we get? Equating coefficient of variation qk. So here is 1, here is 1, and here is 1. What do we get?
We will get pk minus
delta
delta.
f by delta small qk,
Yeah.
small qk, then
Equal to pj
equals to pj
times delta qj by small
delta qj by delta small qk.
Okay. Yeah.
So we can change it a little bit and finally write delta f over delta qk equals to pk, small pk, minus big pj delta qj over delta small qk.
Yeah.
Okay. So, and also what happens to the other part? Variation of pk
Minus
minus
delta
delta f by delta pk equals to
pj times
pj times
delta qj
qj by delta
pk.
pk.
Yeah.
So it basically gives you the same thing, like you just take the minus sign on the other hand. So it gives you this. So we want a transformation and also a f that actually satisfies these two relations, right? Then it will be fine. Like if we can find a f that satisfies this relation, then actually that's equivalent to saying that we are actually we are able to find a pq that actually transforms this pk variation qk minus variation f into just a whole thing like pj variation qj. Like saying finding an f that satisfies these two equations is equivalent to finding a transformation rule that satisfies this thing, right? Those are equivalent actually.
Yeah.
We derive one from another. Okay. Now, considering those relation, all we need to do, we need to substitute that inside our old S bar. That's the goal. So we have relations. We have here like what is our small pk and what is delta f by delta qk, what is delta f by delta pk. We want to substitute those results inside of S bar, remember, here. So S bar was nothing but integration T1 up to T2. I'm writing the full form. So pk qk dot minus, it was h, also then it was minus df over dt, right? So I'm writing the df over dt first. Then I'm writing h. Actually, I should write the dependency explicitly as well. So ddt of f that is dependent on q, p, and t, and then minus h, which is also dependent on q, p, and t, dt. This was our S bar, right?
Yeah.
So take this time derivative explicitly and write down what you get. Write down what you get. So take the derivative. What do you get?
Derivative of the f term, right?
Yes, ddt of f.
Yeah.
ddt of f. So what is that?
Is minus
Minus
del f
delta
by
by
del qk.
delta qk. It's not
Delta.
del, it's delta.
Yeah. Sorry. Delta
Yeah,
qk
delta qk. Then
times delta qk.
just delta qk, or it's qk dot, like time
Oh,
derivative of
yeah, qk.
then minus delta f by delta pk, time derivative of pk, right?
Yeah, pk dot.
Then it's also dependent on time explicitly, so we need to consider that thing as well.
Yeah.
And then we have our h, which is dependent on q, p, and t. So this is the whole thing. Now what we are going to do is to substitute that delta f over delta qk and delta f over delta pk here that we got just from the previous relation, like here.
Yes.
Right? So just substitute those. So we get T1 up to T2. It will be a little bit longer line here, longer expression, minus what is delta f over delta qk? What is delta f over delta qk? It's pk minus that whole thing, right? So it's pk minus pj, big pj, delta big qj by delta, what was that? Delta qk.
Yeah.
Delta qk, and then qk dot.
Yes.
And then minus what is delta f over delta pk? What is delta f over delta pk? That's nothing but pj delta qj by delta pk. So it becomes positive.
Yeah.
And pj, big pj, delta big qj by delta pk, like that. Then small pk dot, because we have this thing here, and now just write down everything else. Delta f over delta t minus h as a function of q, p, and t. Okay, at this point, do you see anything that can be combined into one single stuff? Look here, q is a function of coordinate momenta, like big Q is a function of old small coordinate, like small q, small p, and t. So can you collect these terms into single one, single something? So let's do the algebra, right? Let's do the algebra.
Minus signs canceling.
Yeah, the first term cancel with the second one, right? This term like pk qk dot, and we have negative pk qk dot, that cancel out.
Yeah.
These two terms cancel out. Are you guys following me here? Like,
No, not yet.
Yeah.
Yes.
were you able to follow this? Okay, so these two terms, they cancel out, that's for sure. Then we can write the third term directly. So third term is this minus sign, and that minus sign gives you a positive. So we end up having pj delta big qj by delta small qk dot.
Yes.
Right? And then we have plus big pj delta big qj by delta pk dot.
Yes.
And then we have minus delta f by delta t minus h, which is a function of q, p, and t dt. We can write like that.
Yes.
Okay. So now, so let's do a side calculation. So what is pj dot, like time derivative of this thing? What is this?
This
Change
is
it. Mhm. What does it give you?
Del Qj, delta
Delta
Qj,
Qj by delta small qk,
Qk.
qk dot
Yeah.
plus
Delta Qj,
delta qj by delta
delta Pk,
pk,
and delta
pk
Pk dot.
dot. Then plus
Then delta plus delta
partial
Qj.
derivative of q with respect to time. Hmm?
Yeah.
So as you can see, if we factor out this pj in two terms, this is basically that term, right?
Yeah.
So we can write these two terms equals to basically dqj by dt minus delta qj by delta t. You can write like
Yes.
that. So
Yeah.
that's we are going to substitute. Remember, qj dot is basically dqj over dt. So we can write integration t1 up to t2 pj qj dot, which means the total time derivative, and then minus pj delta qj by delta t. Then we have minus delta f by delta t, and then we have minus h, which is a function of q, p, and t.
Yes.
Okay, now we are almost done. So let's define our big K, which is a function of big Q and big P and T, big Q and big P and T, that is the rest of the term, that is H, Q, P, and T, then minus, no, not minus, it's plus delta F by delta T. Basically, F is a function of Q, P, and T, and then plus Pj delta Qj by delta T. If we define like that, what do we get? Like we are calling this whole term
Yeah.
is our
K.
K.
New Hamiltonian. Yes.
Yes. So we get S bar to be T1 with this definition, T1 up to T2, big Pj, big Qj dot minus big K of big Q, big P, and T dt. This is our S bar. So just varying this thing will give us the equation of motion, right?
Yes.
So let's vary that and see what happens.
Okay.
So if you vary that, what do you get?
I will get variation of this integration, which is basically I can give it inside the integration because it is variation of it.
Yeah, it gives you T1 up to T2. Then
Pj times variation of Qj dot.
yes, Pj variation of Qj dot minus plus Qj dot variation of Pj
Then variation of
then minus delta K by delta. Let's write Qj,
yeah.
variation Qj, then minus delta K by delta big Pj, variation Pj.
Yes.
Okay, now we can integrate this thing by parts, and we can get finally integration T1 up to T2. What do we get? Qj dot minus delta big K by delta big Pj variation big Pj, then plus minus the other one, right? Like big Pj dot minus delta K by delta big Qj variation big Qj, and then we have again the boundary terms, which is
But we should write dt before writing the boundary.
Yes, means dt. Yeah. And then we have the boundary terms, that is Pj variation Qj, but that is evaluated on the boundary.
Yes.
Okay, that is exactly in the form of Hamiltonian mechanics. So even if we cannot see at this point that how this variation Qj becomes vanishing, we may not see it, but we'll see it later. So this is so far we got, right?
Yes.
Okay, so
By variation of delta Qj vanishes at T1 and T2 at boundary.
no, you cannot tell that, because
yeah.
that's a function of, like, only thing we are imposing, that is this thing, that variation of small q at T1 equals to variation of small q at T2. This thing equals to 0. This is the thing only we are imposing here.
Yeah. Okay.
So to see that, actually we need to evaluate that variation of Qj explicitly in terms of coordinates, actually.
Okay.
So in terms of coordinates, variation Qj, what do we have? This is delta Qj by delta small qk variation qk. And then
Yes.
Then
Delta Qj
plus delta bqj by delta
delta Pk variation of
pk.
delta Pk. Yeah.
Okay. So obviously this term vanishes, that's for sure, because it has variation qk explicitly inside of it. But that's, for that term we're not so much sure at this point, at least.
Yes.
So if you substitute that delta qj over delta pk, so
but
we have,
why we are not writing the time part at the variation of delta Qj? Because delta T equal to 0.
no. T is a parameter. You cannot vary a parameter.
Okay.
T is just a parameter. It's not a distribution or a function. You vary a function that is dependent on something.
Okay.
So far we only have one question in our hand, that is how this thing vanishes at this context. So let's take a break. We'll come back within 5 or how much time should we take a break? 10 minutes?
When?
All right.
Yeah. So yeah, if you have any question, you can ask.
Are you going to give an example with this new transformation?
Yes.
Okay.
I'm going to give at least few examples. That's actually I'm looking into that. Is there any like simple example that I can show directly? So if you have any question, just ask. All complicated things.
I want to see the first line showing on the screen.
First line.
Yes, now it's okay. Now it's okay. Okay.